In this video, I would like to illustrate some principles of multimodal system development. I will first concentrate on empirical development possibilities and then on model-based development possibilities. In order to develop a multimodal interactive system on the basis of data, we need to collect data. And the first way to collect data is to observe human-human interactions for a comparable task the multimodal interactive system has been built for. This has some disadvantages because user behavior is usually not the same in a human-human interaction than it is in a human-machine interaction. So users behave differently when being confronted to a machine than they would behave with a human. There are also, in a human-human interaction, no or very few recognition and understanding errors, and in many tasks there is actually no comparable human-human interaction situation which the human-machine interaction could be based on. This is why people have developed this second technique, which is called the Wizard of Oz technique. A Wizard of Oz is actually an expert which replaces parts of the system by simulating a human experimenter. And of course the term comes from the famous novel from Baum. This wizard has to behave exactly like the future system or the system component the experimenter is intended to replace would behave. So he could not behave as a normal human, but he should behave actually as the future machine will behave. It may also replace only parts of the system, so modules of the system, and other parts may be implemented already. Then we talk about a bionic wizard. The parts which are replaced by the wizard can be illustrated in the picture behind me. In a classical, for example, spoken dialogue system, you would have a wizard replacing a natural language generation component and a dialogue manager. And as soon as a text-to-speech synthesizer becomes available, then perhaps also this component here can be taken over by the machine. If we have a multimodal interactive system, we might want to also address other modalities, for example, gesture recognition, face recognition, and things like that. It might also provide some output, additional output capabilities, like a graphical user interface. Then we're talking about an extended Wizard of Oz scenario. Such a Wizard of Oz setup can be quite complicated. Here you see a view of a Wizard of Oz setup from the human participant's point of view. So you see that the human is sitting in front of a computer, multimodal computer interaction. It is observed by a couple of cameras. We have a camera which shows the face view and a camera which shows the interaction and the hands view. We also have a screen recording equipment and so on. Of course, a microphone put on the table so that we can follow what the test participant is doing. And on the other side, there might be one, or in this case even two wizards, which observe and which simulate parts of the system. Simulation may, for example, be split into one experimenter doing just the transcription of what the user said, so replacing the speech recognition component, and another one generating the behavior of the interactive system, so replacing the dialogue manager component. But there might be different setups according to which components of the system have already been implemented and how well they work. The second type of technique for developing multimodal interactive systems is based on models, that is, algorithms which intend to describe human behavior. Such a model can be used for making assumptions about the next interaction step, but they can also be used for training, for example, a statistical dialogue manager or for evaluating without relying on human test participants. So you see that the purpose and the application areas of such models are multifold. There are different types of models with different aims. Usually we distinguish between statistical models that are models learned from data, for example using reinforcement learning. Partially observable Markov decision processes, or POMDPs, would be an example of this type of model. And on the other hand, rule-based models, which describe human interaction behavior via rules. There are also hybrid models which combine statistical and rule-based approaches, as we will see with the MeMo workbench at the end of this video. A very popular class of model is the so-called cognitive architecture. Actually, cognitive architecture tries to represent hypotheses about human cognition. That is, they are based quite upwards in the human decision-making process. These models require knowledge about how to conduct a task, and this is knowledge which usually an expert needs to provide to the model in order to be functional. We can distinguish between so-called high-level architectures with a relatively coarse temporal resolution, GOMS would be an example of this class, and low-level architectures which describe interaction behavior in terms of atomar events. EPIC or ACT-R or SORA would be examples of these low-level architectures. In order to implement these architectures and to make them useful for simulating human-machine interaction, tools are available, for example GLEAN or CogTool. Unfortunately, it is so far unclear how modality-specific rules, for example rules for modality selection, can be included in such models. There are very first approaches by Schaffer, which try to model quantitative decision-taking on modality selection. A very popular such cognitive architecture is ACT-R, which you see in the picture behind me. ACT-R is based on a production engine, which is at the center of the picture here, which is matching, selecting, and executing certain productions in terms of interaction steps. This machine interacts with buffers for the goals, for the retrieval of information from memory, for the visual information, and for the manual information. And for each of those buffers, there are modules available which describe how the interaction actually would work. And some of those modules then have a connection to the external world. These models have been used to describe interaction behavior, but they are not very popular so far in practically building multimodal interactive systems. A model which has the aim to be practically usable is the so-called MeMo workbench, which is an example for the hybrid approaches I depicted at the beginning of this video. The MeMo workbench makes use of a user model, a task model, and a system model in order to simulate human-machine interaction behavior. The system model is very easy. It can be deduced from the machine description, the task model as well, because we know what the multimodal interactive system has been built for. And then there is a user model. And the user model then tries to use the task model in order to turn this into a probable sequence of steps a user would perform with the help of the system. I'm talking about a probable sequence because such a user model may generate many different interaction paths with different probabilities, and these interaction paths are manipulated by rules. These rules are governed by either user characteristics, for example, a user who has certain preferences for certain interaction modalities, who has certain knowledge, who is used to, has experience with certain interaction techniques, but also rules which are governed by the characteristics of the system. That is, whether there are one or two or many buttons on a web page or alike. Then, using these models, typical user-machine interactions would be simulated, they would be logged, and on the basis of the log files, we can evaluate how well these interactions work. That is, we can, for example, determine the task success, we can determine the efficiency of the interaction, but perhaps also if a user has to step back several times in the flow of the interaction, then this might be judged as bad. So we might be able to provide a full usability profile of the simulated interaction between the user and the system. In order to describe some specific characteristics of the user, there might be rules being implemented in such an approach. For example, a rule for predicting the execution time, which you see here, which is actually based on Fitts law and which illustrates how long a user will take in order to find a certain icon on a screen and then click that icon on the screen. These rules may be used in the MeMo approach, but they might also be attached to a cognitive architecture like ACT-R.